A ray of violet light with a frequency of 7.69 times 10 to the 14 hertz, moving through diamond, enters water at an angle of 30 degrees relative to the normal drawn from its point of entry. Before even reading the questions, they tell us a couple of things here. First, I know that this 7.69 times 10 to the 14 hertz is my frequency because hertz is the unit for frequency, so that's my F. They tell us that we are going from diamond into water. So diamond is going to be my first material, water will be my second. They also tell us that we are entering the water at an angle of 30 degrees, which means we're going from diamond into the water, so this 30 degrees is going to be my theta 1. Okay, so now what is the speed of this wave in diamond? The formulas that we're going to use are found on the reference table on page 5 under waves. We have a couple of formulas that we can use, a couple of formulas to choose from. So first, the first formula that we have here, we talked about the other day, which is the formula for reflection. Theta I is equal to theta R. Your incident angle is equal to your reflected angle. We have something that is called Snell's law, which is N1 sine theta 1 equals N2 sine theta 2. And this will help us in when we are trying to determine the refracted or incident angle given the materials that we have. We also have a formula in which we can solve for the speed in a given material, and that is N is equal to C over V, where C is the speed of light. Speed of light, which is found on our reference table. And then the last formula that we have is N2 over N1 is equal to V1 over V2, which is equal to theta wavelength 1 over wavelength 2. So these are all of the possible formulas that we can use when solving for the questions here. So now if I go back and I look and it says, what is the speed of this wave in diamond? Well, I'm looking for speed. I know that I have diamond. On our reference table, diamond, the index of refraction for diamond is 2.42, no units. We are looking for speed. And of course, we always know C, which is 3 times 10 to the 8 meters per second. I'm going to use the formula N equals C over V. We have 2.42 is equal to 3 times 10 to the 8 divided by V. To make this easy, we cross multiply, we divide, and we end up with V equals 1.24 times 10 to the 8 meters per second. This is the speed of my wave in diamond. Next, we want to know what is the wavelength of this wave in diamond. So now we're looking for lambda. I'm going to go ahead and I'm going to use our basic wave equation because we have all of these equations we can possibly pull from. Our speed of this wave we just solved is 1.24 times 10 to the 8 meters per second. I know my frequency is given to me in the problem, which is 7.64 times 10 to the 14 hertz. And we are solving for wavelength. Solving for wavelength, we end up with 1.61 times 10 to the negative 7 meters. Next, we're looking for what is the wavelength in water. Well, now I know that I'm in diamond, so I know that the index of refraction for my first material of my diamond is 2.42. They ask us for water. The index of refraction for water is 1.33. I'm looking for the wavelength of the water, which is my second wavelength, and we just solved for our wavelength 1, which is right here. I'm going to go ahead and I'm going to use the formula N2 over N1 is equal to wavelength 1 over wavelength 2. Going through, we can plug in our information, so we have 1.33 divided by 2.42 is equal to 1.61 times 10 to the negative 7 meters divided by wavelength 2. Solving for wavelength 2, we end up with 2.93 times 10 to the negative 7 meters. That's the wavelength of my wave in water. Next, will the ray speed up or slow down as it enters the water? Well, I'm going from an index of 2.42 to 1.33, which means that it's much less dense. And if it's less dense, I know that my speed is going to speed up. What does this mean for the angle of refraction? Well, if I am going from, again, 2.42 to 1.33 in terms of my index, and again, I'm going from a high index to a lower index, that means that my wave is going to bend away from my normal. So theta should increase, and my wave will bend away from the normal. Again, you're going into a less dense medium, so you have more room to move. At what angle will this ray refract when entering the water? Okay, here, if I'm looking for an angle, the only formula that we can use, n1 sine theta 1 equals n2 sine theta 2. n1 is my diamond, which is 2.42, times the sine of my 30 degrees that was given to me in the problem of how I entered into this boundary, is equal to n2, which is my water, 1.33, multiplied by the sine of theta 2. The first thing we want to do is want to get sine of theta 2 by itself. So divide 1.33 on both sides. When we go ahead and we do that, we end up solving for, let's see, grab a calculator, 2.42 multiplied by the sine of 30. Make sure your calculator is in degrees. Divided by 1.33, we end up with 0.90977, this big long number. You want to make sure that you are writing out the whole thing. We don't want to round. So we end up with 0.9097744,361. And this is equal to sine of theta. Oops. Oh my goodness. How do you go away? There we go. Sine of theta 2. Okay. We are looking for an angle, which means that we are going to use our inverse sine function, and we are going to do sine of the negative 1 is equal to, use the answer button. I wrote out this whole long decimal here just to show you. I would never write that on my paper. Use the answer button on your calculator. Don't round so that you can take the whole thing. And this is going to be equal to theta 2. And if you do this correctly, you are going to end up with 65.47 degrees. So theta 2 is 65.47 degrees equals theta 2.